Okay, it is time to get started. So what we'll do today is, on Tuesday, I did not feel comfortable with the explanation of the answer to question number 1 in the test. So I went home and I really kind of thought about it and tried to come up with another way to explain it. And that would be the first part of today's lecture, is a re-explanation of how to solve that problem. And hopefully by talking about this one and also the lotto problem, which is an easier problem in a way, we can just kind of learn more about how to solve problems like that, how to apply combination and how to apply permutation when we're dealing with certain types of problems. Okay? So that would be the first part of today's lecture. The second part of today's lecture is going to be finishing up the encryption stuff that we started on Tuesday, okay, which I think is kind of interesting. Today we'll talk about key pair encryption, where one key is called a public key, where everybody can use to encrypt a message, and one key is called the private key, where the person who owns the private key, only that person can decode messages encrypted by the public key. So we'll talk about that today, and if we have any time left today, we'll talk about search algorithms in graphs. In other words, if someone gives you a graph and say, I'm here on this particular vertex, but I want to be over here on this vertex, how do you find a path and how do you find a shortest path? So we'll talk about a few algorithms that can do that part. So that would be kind of the schedule of today's lecture. So let's go ahead and get started with combination and permutation. And I kind of know that some of you are kind of sick and tired of permutations and combinations, but it is a very important topic, not only in computer science but also in statistics. So understanding how to break a problem down to use combination and permutation correctly is going to be useful, not only in this class. So we'll start with the main concept itself, okay, themselves. The main concept of C, or the combination C and R, is the number of ways to combine R things from N things. So we apply this when we have to select certain elements from a set to make subsets. Okay, that's basically what it is. In other words, if you have a set of a certain number of elements and your objective is to make subsets out of that set, and N is the number of items in the original set, and R is the number of items in each subset, C and R will tell you the number of possible subsets they can make. Because ordering is not important in a set. Is that making any sense? So to give you an example, okay, we can look at a particular set, let's say A, which has 4 elements, A, B, C, and D. And I want to create subsets, each one only having 2 elements out of this particular set. So how many subsets can I make out of this? Well, we can have AB as one subset, we can have AC as a subset, AD as a subset, and then we move on to BC, BD, and then we move on to CD. But that's it, okay? So 4 choose 2, would basically have, okay, if we just kind of spell out everything, BC, BD, and then we have CD, so we have 1, 2, 3, 4, 5, 6 items. 4 choose 2 is 6. Does that make any sense to you? Because it is 4 factorial divided by 2 factorial, and then 4 minus 2 factorial. This is just the formula to calculate the number of combinations. Does it come up with 6? That's the question. Well, 4 factorial is 4 times 3 times 2 times 1, which is 24. 2 factorial is 2, and 4 minus 2 is 2, and then the other 2 factorial is also 2. So we have 24 divided by 4, which is exactly 6. So are there any questions about the basic concept of what is a combination? It's when you have to choose something and then the order is not important. Permutation is basically the other part where you are still choosing R things from N items. But in this case, the ordering is important. So we are looking at permutations and not combination in this case. So you can look at it, from the terms that we have already used. We are no longer constructing subsets out of items from a particular set. We are creating tuples. Okay, Because when in a tuple, what is the main difference between a tuple and a set?
The ordering matters.
The order matters in a tuple, okay? So we are creating, we are calculating the number of ways to create tuples of a certain size from a particular set. That would be permutations. So the difficulty is not with the main concepts, but to decide when to use which one, and also how do we combine these things to solve problems where you need to use a combination of these concepts. So the next paragraph talks about in discrete probability, in general, we talk about things like this. Okay, we talk about the probability of A is something. But in this case, what we have is A is a particular set. So we are looking at the cardinality of A divided by omega, which is another set. And we are looking at the cardinality of omega. In other words, the probability of A is basically, by definition, the cardinality of A over the cardinality of omega. But these two sets, they have to have a certain relationship, because A has to be a subset of omega, doesn't have to be a proper subset, only has to be a subset. In other words, in the extreme case, A can be the same as omega, in which case you have a probability of 1, okay, all the time. So now we go to talk about what is omega and what is A. So omega, which has, in this case, nothing to do with a big O notation for time complexity estimate, is a set of all possible outcomes. In other words, if you look at all the possible things, all the possible ways that things can happen, that's the set of omega. A is a subset of omega. That would be the things that we are actually interested in. Okay. The next paragraph gives us a particular example. A may represent, getting 2 queens out of 4 drawn cards, out of playing cards. So you have a full deck of playing cards, and instead of asking what is the probability of getting a queen of hearts, queen of spades, and then a 2 of club and a 3 of, what is the remaining one? Diamond. Okay. So instead of asking the probability of one particular outcome, which is useful, I want to collectively calculate the probability of just getting any 2 queens out of drawing 4 cards. Okay, but that becomes a set of certain members of elements of omega. Are we still doing okay so far with this concept? Okay, so that's why sometimes we want to use a subset instead of a single element when we calculate the probability of something. So these are the general concepts, and then we apply those to the problem in your second exam, the birthday shared by R out of n people problem. So in this case, I generalize the problem. Instead of having 2 as R, I just say, okay, we have R people within n people sharing the same birthday, and nobody else is going to have the same birthday as anybody else. Okay. So how do we analyze this problem? So the way we analyze this problem is we have to consider all the possibilities first. The possibilities are basically a set of n tuples where each element of the tuple represents the birthday of a particular person. So if you want to consider a simple example first, okay, we can consider an example of 5 people. Okay, there's a total of 5 people. So we have a tuple that has 5 entries. The first entry represents the birthday of the first person, the second person, third person, fourth person, and the fifth person. But once we associate a position in the tuple with a particular person, that tie does not change. So that's why this is position sensitive. It is a tuple, it is not a set. Are there any questions about this part? Okay. If I don't care whether people share the same birthday or not, okay, what is the number of possibilities when I have 5 people and each person has a birthday, and we'll just only consider 365 days in a year. So how many possibilities are there when we have 5 people in the class, and what is the total number of possibilities?
I think I choose 2.
No, you're not choosing anything, because we are just basically saying okay, we have 5 people in the class, okay, and we're just asking if you consider all possibilities, they can have the same birthday or not. Okay, I don't really care one way or another. How many possibilities are there? Exactly, 365 to the power of 5. Because we have 365 choices for the first person, 365 choices for the second person, and so on. But they are independent. In other words, the birthday of the first person has no influence whatsoever on the birthday of the second person or the rest of the entire group. So that's why, when you look at the set of all of these tuples, the cardinality of this omega is 365 to the power of 5. Is that okay so far? Now this is closely related to your homework assignment, because in your homework assignment we are talking about a group of 30 people. So instead of the 5, we have 30 as the power of 265. That represents the total number of possible outcomes. But we are not interested in all of the outcomes. We're only interested in the outcomes where a certain number of people share the same birthday. Are we doing okay so far with that? Is that okay? So when you look at the set A, okay, in this case, which is the set of all of the outcomes that we are interested in, we want this particular set to be, let's say, 2 people in the class or within these 5 people sharing the same birthday, and then the other 3 people all have unique birthdays. They do not share a birthday with anyone else within the 5 people. Are we doing okay so far with that? Which is kind of like a particular application of the exam question. Are we doing okay so far? Okay. So that means, when you look at 5 people, and instead of using exact dates, okay, we'll deal with how to choose dates at some point. But at this point, we'll just say, okay, if you want 5 people in a class, and any 2 people can share the same birthday, so how many unique birthdays are we talking about within these 5 people? 4 unique ones, right? Okay. So we'll just say that, okay, we'll pick A, B, C, D, E, A, B, C, D to be the 4 birthdays, the 4 unique birthdays. We know that these 4 are all different. They're not common. So now the question is, how many ways can we not combine, but how many ways can we arrange A, B, C, D to come up with scenarios where you can have A, B, C, D, and then you can have A, B, C, C, D, and so on and so forth. That's the first question that we have to answer. We'll talk about how many 4 birthdays can we choose out of 365 days later, but this is our first problem. So in the notes here, which I wrote last night, that would be quote unquote the first problem. So the first subproblem is given n minus r plus 1 unique birthdays, n being the total number of people in the group, r being the number of people who share the same birthday. So we have n minus r plus 1 unique birthdays because several people are sharing the same birthday. How many ways can we assign these unique birthdays to these n people? That's the first question. So how would you go about calculating this number? I mean, it's kind of spelled out in the notes too, so we can either read from it or you can kind of think about it a little bit, and then we'll talk about it. Do you guys want to kind of think about it a little bit first? Well, it's not exactly. Well, it is 4 factorial. It is 4 factorial because it is p of the number of permutations of choosing n minus r items out of n. Okay, so in this case it would be it's not 4 factorial.
This is like how they get ordered based on a fixed digit. So you have 4 factorial different combinations of these like moving around.
Okay. Well, there are 2 ways to look at this. The first way to look at this is, we can say that there are n but non-unique birthdays to assign to n people. Okay. In other words, instead of looking at 4 unique birthdays, we kind of say that, okay, we have A, B, C, D, E. There are exactly 5 birthdays to assign to 5 different people. So in that case, it is 5 out of 5, but you're looking at permutations because the combination of A, B, C, D, E, or the permutation or the arrangement, this tuple is considered to be different from the tuple of B, A, C, D, E, right? So that's why we have exactly 5 factorial. But that is not going to work out completely because 2 of these people share the same birthday. Are we doing okay so far? So when you look at each one of these patterns, okay, it's going to be common with at least one other permutation because 2 of these numbers can be the same. Are we doing okay so far with that?
So like A can equal B, for example.
A and B can be the same. So when A and B are the same, then these 2 permutations are basically the same permutation because A and B are being the same. So now the question is, out of 5 factorial permutations of assuming all of these birthdays are unique, out of these, how many or what is the number of repetition?
N minus R plus 1.
Well, the number of repetition is going to be C, 2. The number of repetition is going to be just 2 factorial. That's the number of permutations that are duplicates of each other.
Which is only A, B, A, C, A, D, A, E. I don't quite get that.
Okay, so when you look at 5 things, okay, and of which 2 things are the same, so now you basically ask, how many unique patterns are we getting? How do we get this 2? Because we have 2 people in the class sharing the same birthday. 2 out of 5 people are sharing the same birthday. So out of A, B, C, D, E, 2 of those numbers, let's say A and B are the same. Okay, so AB and BA are now considered the same. 2 factorial is basically representing how many ways can you spell out A, B, how many ways can you arrange A and B. Okay. Is that okay so far?
That makes more sense.
If you had 3 people, it would be 3 factorial.
Yeah.
Correct. Yeah. So we have 5 factorial as a total, but we know that there are repetitions like in terms of 2 factorial. So the total number of unique ways to arrange these tuples is going to be 5 factorial divided by 2 factorial. Yep.
Why would it be 5 factorial minus 2 factorial?
It's not minus because it is. Sorry, go ahead.
It just takes out 2 cases if you minus it.
It's for
Doesn't make
every
another
2 cases. Every 2 cases is representing 1 unique case. Okay, let's.
Oh, I see. Oh, yeah. Okay.
Is that okay?
Maybe you should explain it.
Okay, differently.
Yeah.
Okay, is everybody getting this part? Because I know this can be a little bit confusing. Hmm? You're confused. Okay. Maybe what we can do is to use a mouse pad here and actually spell out some. Oh, that's not it. Accessories, mouse pad. Back to my notes. Okay. All right. So we are considering a group of 5 people, and we want to have 2 people sharing the same birthday, and then the other 3 must have unique birthdays. Okay, that's the situation that we are in. So out of 5 people, we have A, B, C, D, E, B, A, C, D, E. We have A, B, D, E, C, So I'm just going to give you a few examples, because 5 factorial is 120. It's going to take a long time to list out all of these cases. So I'm just going to give you some, some cases here. So we have a C, E, C, D, E, and I think 2 more would be should be enough. Okay, so we'll have a D, C, D, A, B, E, and then we have C, D, B, A, E. Okay, now these are chosen, in a particular way, so that I can use it to explain the concept that we have, at hand. Okay, so this is only a small sample of all the permutations of choosing 5 out of 5 items. Okay, is that making any sense?
In a certain, choosing them in a certain order.
No, this is kind of somewhat random. I mean, there's no particular system of choosing these 5 permutations out of 120. But this is just a sample. Okay.
Well, what I mean is they're each in a different order, somewhat.
Correct.
Okay.
Order is important. That's why we are counting permutations, because each item in a tuple is representing a person in the class. So I'm trying to calculate, if I just choose 5 different birthdays, okay, 5 birthdays, and have to assign these 5 birthdays to 5 people, how many ways can I arrange that? Is that okay so far? Okay. All right. So now, once we have this long list of 120 items, now I tell you, hey, you know what? A and B are really the same. Okay? And then I ask you, if A and B are the same, what would be the total number of unique tuples in this, in these 120 tuples? That's really is a question. Okay? No, it's 100 divided by 2. So the actual number is 60. Because if A and B are really the same, then these 2 items would basically combine to just 1, right? So it becomes A, C, D, E, and this one is irrelevant. These 2 will combine to 1. Okay, these 2 rows will combine into 1, which is A, D, E, C. And then these 2 rows will combine to 1, and that will be C, D, A, E. Is that okay? So every 2 rows combine into 1, and we have 160 rows to begin with, and that's why we end up with only 60 rows. That's why we are dividing and not subtracting. Is that kind of okay so far? Now, this is kind of like just a sample of all the possible cases, but you have to kind of think about cases where we originally, let's say, we have A, C, D, E, and then the B at the end, and then B at the beginning, C, D, E in between, and A at the end. You know what? These two rows will still combine into one single one, which is A, C, D, E, A. So you basically group things into these groups of 2 in this case, and say, hey, these groups are exactly the same thing. So you combine those, and the outcome is we only have 60 items once we take out all the duplicates. Are we doing okay so far with this? Okay. But dealing with 5 and 2 is relatively easy, because 2 is one of those numbers where 2 is 2, but 2 factorial is also 2. Okay. So now the question is, how do we generalize and say that we have? So the generalization is we have n people in the group. R of these have the same birthday. The rest all have unique birthdays. Okay. So if that is the situation, obviously in this case n is 5 and r is 2. So in general, if that is the case, how many unique tuples are we going to get out of these n tuples? That's the question. So exactly. So it'll be n factorial of ways to arrange the birthdays, but since you have to get rid of the duplicates, for each unique set of birthdays, there will be r factorial duplicates. Is that making any sense? That we can have r factorial duplicates? Because if A and B are duplicates of each other, then we have 2 factorial ways to arrange A and B. If A, B, and C are all the same, then we have 3 factorial ways to arrange A, B, and C. they become all duplicates. Yep.
So basically, if in the group of 5 people, there are any number of people that have the same birthday, it's just gonna be the permutations divided by the number of people that have the same birthday factorial. Like in this case, like n factorial divided by 2 factorial is the number of people or the number of things or ways or unique combinations that you could have of those 2 people having the same birthday.
Okay. Let's restate what we are dealing with here. This is basically saying, given that we have, there are this many ways to arrange n minus r plus 1 birthdays in a group of n people so that r of these people have the same birthday.
Yeah.
Is that okay? The reason why we have n minus 1 plus 1 birthdays is because n minus r is excluding the r people with that shared birthday, but that particular group, that birthday that is shared by r people is different from the other n minus r birthdays, and that's why we have to have the plus 1 at the end. Is that okay so far? Because this is actually one step of the 2-step process to actually calculate the probability, but this is a very important step. Is that okay? All right. So if this is okay, then the second problem is out of a year, okay, which has 365 days, how many subsets of n minus r plus 1 birthdays can we generate? That would be the second part of the question. Because the first part of the question is basically assuming that we have already randomly picked out n minus r plus 1 unique birthdays out of a year. And just we are just interested in how many ways can we assign these birthdays within a group of 5 people. So the second part of the question is asking, okay, now that we are done with assigning the birthdays, the unique A, B, C, D, E birthdays to 5 people, how many ways can we pick out 4 unique birthdays out of 365 days? But that's an easier problem because the problem itself already states the solution. When you're dealing with subsets, ordering is not important. Okay, ordering is not important. So I already say out of a year of 365 days, so we're choosing out of 365, but how many items are we choosing out of 365? N minus r plus 1. Yeah, exactly. So the answer to the second question is just basically the number of combinations of choosing out of 365 n minus r plus 1. Are we doing okay so far with the 2 parts of the question? Yep, go ahead.
And n minus r plus 1, what does it represent? It represents one specific date.
No, it's representing the number of unique birthdays that we need for this particular group of people.
Number of unique birthdays.
The number of unique birthdays that we need for this particular.
If you want a single unique birthday, right? You need a specific date for 3 or 4, how many people you have.
Right. N is the total number of people in the group. All of these people share exactly the same birthday. The rest, they all have unique birthdays.
Okay.
Yep. So this is the number of days we have to pick out of a year so that it will meet this requirement.
So the rest of the group have unique birthdays. If you have 30 people and you want 5 of them have a specific, the same birthday, this calculates how many combinations you need for the rest of the other 25.
This means, not caring who has which birthday, how many ways can we pick out days in a year to represent the actual birthdays of the entire class. Is that okay or not?
Let's see how it looks on the example here.
Okay. Let us take this class as an example. Okay, so all the people in the classroom at this point, including myself. Okay. So what we want is to say, I want to calculate the probability of how many ways can we arrange, things, right? That's basically the principle of discrete probability. So in this case, let's say, let's say we have, 38 people in this class, okay? So in this case, n is 38. And, oops, said one thing and I wrote down something else. So out of the 38 people, this time I'm not interested in exactly 2 people. Let's say I'm interested in exactly 3 people sharing the same birthday. So in this case, R is 3. But everybody else need to have unique birthdays. So how many unique birthdays are we going to have in this class? Let's say this class meets this requirement. So I display the year calendar on the screen or put it on the whiteboard, and I just ask each person to come up to the whiteboard and circle your own birthday. If it is already circled, you can just leave it alone. Okay? So that means how many days in a calendar is going to be circled? It'll be 38 minus 3 plus 1. Okay? That's what the n minus r plus 1 is for. It's the number of circles in the calendar for a given group of people that meets the requirement.
You just add that 1 that specific one that could be 3 or 4 people share.
Right. The plus, the plus 1, quote unquote plus 1 is for the one single day that is shared by r people. So you can look at it that way. So are there any questions about why out of 365 days we are picking n minus r plus 1? It's not a problem, okay? So now we have to multiply those two so that we have a total number of possible ways to arrange things. So now we look at a product. So the product is going to be, oh, by the way, let's clean this up a little bit. What is n factorial divided by r factorial, where r has to be less than or equal to n? There's another way to say this one. Say again?
N minus r factorial.
Yep. Well, it is the same as p n comma n minus r. It's choosing n minus r things out of n, but the order is important. Do you guys still remember the definition of the number of permutations? More or less? Okay, let me just remind you. Okay, so when you look at the number of permutations, if you are choosing k items out of n, okay, and ordering is important, this number is actually n factorial divided by n minus k factorial. So in this case, we have something similar, except we start off with r factorial, and so we can reverse it back into a permutation formula by saying we are choosing n minus r things out of n, where the order is important. Is that okay so far? Okay. All right, so now that we have these two equations, then we can say that there are, we just have to multiply these two numbers, p and n minus r. Okay, these are the number of ways to arrange n minus r plus 1 birthdays amongst n people. But there are this many ways to choose n minus r plus 1 birthdays out of a year calendar. So when you multiply these two numbers, it becomes the total number of outcomes that fit our requirement, which is having n people as a group, and all of those people share exactly the same birthday, and then the rest, they all have unique birthdays. Are we doing okay so far with this number? Yep.
Why is it permutations n comma n minus r?
That comes from the previous two paragraphs. It comes from here.
Isn't it something different from n minus r? Because isn't n5 and r2? So would that be choose permutate 5, permutate 3? Right?
Okay, let's take a look at the number of permutations. Okay, so when you look at the number of permutations, the number of this is too faint. I have to hide this from the other professor. so when you look at the number, and this kind of faint too. Okay, I'm gonna use the mouse pad. So we'll roll down here. So if you want to look at P and R, okay, which is choose the number of ways to choose R items out of n, but we are considering tuples where ordering is important. What is this equation? It's n factorial. Okay, let's spell it out. Okay, it is n times n minus 1 times n minus 2 times all the way to what? Not all the way down to 1, unless r is 1. N minus r. So when r is 0, okay, then it is the same thing as n factorial. No, that doesn't make any sense.
N minus r plus 1.
N minus r. Oh yeah, that's a minus 1 here. Okay. Okay, so if you look at the number of ways of choosing 35, from 35, if you want to choose 5 items, it is 35 times 34 times 33 times 31, 32 times 31. So, yep, the last one is, there's a plus 1 in here. Okay, so that means my calculation is off by 1, because in this case, there's also it's off by 1. I just have to figure out which way is off. I think it's that.
Yeah, 5 minus 2 minus, or 5 minus 2
Is it correct?
It was correct.
It was correct.
Definition n factorial over n minus k factorial.
It might be clear if you just work it out.
Oh,
just
yep.
plug in the n of n minus r.
Yep.
It'll show this n minus parentheses.
Yeah,
n
because
r.
it's a division part,
Turns
right?
into just n over
So the
r.
part that I got rid of is the correct one. Okay. So to work this out completely, we can say this is the same thing as n minus r factorial divided by n minus r factorial. Is that okay? Well, first of all, if you just look at this portion, what is the value of this portion? It's 1, right? Okay. But what if I group it differently? In other words, what if I group it so that this part is evaluated first, and then the division is evaluated later? What is the other name of the highlighted portion?
N factorial.
It's just n factorial. So n factorial divided by n minus r factorial is the number of permutations of choosing r out of n items. Is that okay? No? Okay.
Is that entire thing over n minus r
Well,
factorial?
it's commutative, right? This part is.
Oh, okay.
So whether I perform the division first, okay, let me just copy and paste it. Okay, so I think we all agree that this is okay, right? Because n minus r factorial divided by n minus r factorial has got to be a 1. And anything can multiply by 1 and get itself back. So the second line is going to put the parentheses in a slightly different way, which is this way. Is that okay? But that basically boils down to n factorial, because this is the first part of n factorial. This is the remaining part of n factorial. It picks up from where it left off with n minus r plus 1. Is that okay?
I'm not convinced. I don't see math.
We have like 2n minus r.
Hmm?
Would be the 2n minus r.
Okay,
multiplied.
let's go ahead and spell this out, okay? Let's spell out n minus r factorial. What is n minus r factorial? It's n minus r times n minus r minus 1 times n minus r minus 2 all the way down to 1. Is that right? Okay. Isn't that just n minus r factorial? Is that part okay? Does it seem to hook up with the rest to become n factorial?
No, the left part is what's confusing me. how is n times n minus 1 times n minus 2 times that, but that n minus r plus 1 n factorial?
That is not n factorial. You have to combine it with the other part first. So what we are looking at is this entire part is n factorial. I wasn't done here yet. I think that's the confusion because I wasn't done here yet. That's the finished form. Because we combine this part here, this entire part becomes n factorial. But the other part, which is here, is just n minus r factorial. So the whole thing can be rewritten as n factorial divided by n minus r factorial. Is that okay?
I think.
Okay. So if this part is okay, then we can go back to here and establish, this relationship. Because n minus r is the complement, is the other part of n.
What would be the term before n minus r plus 1?
Say again?
What would be the term before n minus r plus 1?
N minus r plus
Yeah,
1?
must be-
That'll be
must be-
n minus r plus 2.
Take in the first
Okay,
part.
let's use some real numbers for this. Okay, so let's take this one as an example. Okay, so forget about this part for now. Okay. What is the other way to spell this out? Okay, let's think about it. 35 times 34 times 33 times 31 times 31 times 32 times 31 times 1. Would that be okay? All right. So let's change that 1 into, oops, place to paste. Let's change this 1 to, let's say 30 factorial divided by 30 factorial. Would that be okay? And now we say, let's go ahead and rewrite this and regroup things a little bit so that we take out this parenthesis here, take this one out, put a close here, and put an open here. Would that be okay? Is that okay? And then we spell out 30 factorial just a little bit. So we have basically the same thing. But then we spell out 30 factorial to 30 times 29 times 28 all the way down to 1. Is that okay? Then when you look at the entire numerator, what do we get? 35 factorial. So it becomes 35 factorial divided by 30 factorial. Is that part okay? So you can see, how 5 plus 30 is 35. So they're basically complements of each other. And that's how we can get back to the paragraph that we were talking about here and establish this. Is that okay? All right. So are we now convinced that there are this many ways to arrange to have a group of n people of which r people have exactly the same birthday? Is that okay? So once again, the first component. Yep.
How do you know to just multiply the two portions together?
Because this determines how many ways can we circle n minus r plus 1 days out of a calendar. Okay? But what do we do with all of those circles? For each way of picking n minus r plus 1 days out of an entire calendar, what are we doing with those, circled days? Well, we try to assign those to people in the group. But how many ways can we assign those circled days to a group of n people so that we have r people sharing the same day? It's p, n, comma, n minus r. So that's why they're multiplied, because one determines one thing, but out of that one single combination of certain days in a calendar, there are this many ways to distribute or assign to a group of people. That's why they're multiplied. That's a good question, but it is also, it's important to the understanding of this whole thing. Okay, so there are this many ways to pick days in a calendar and assign to a group of n people so that r of these people share the same birthday. The rest all have unique birthdays. There we go. All right, so we're almost done, okay? This is the number of elements in A, which is the subset that we are interested in. But what is the size of the omega? The total number of outcomes. 365 to the power of n in this case, because we have n people in the class. So the actual probability in this case, PA, which is by definition the cardinality of A divided by the cardinality of, I have to spell omega because I cannot type the omega symbol here, is going to be this number divided by 265 to the power of 30. Up to the end, yep. To the number of people in the group. So that's the more general solution to the problem in exam 2. In the exam 2, n is 30 and r is 2. Is that okay? I mean, is that a better way to explain it compared to Tuesday? But I think the most crucial part is to break it up into two separate parts. The first part is how many ways can we circle n minus r plus 1 days out of a calendar year, okay? And then the second part is saying, okay, once we have those particular dates picked out, how many ways can we assign those dates to people in the group? So when you break it up into two parts, then one side you have to use combination because ordering is not important. The other part you have to use permutation because ordering is important in the second part. Is that okay? Alrighty. Okay. So if this is okay, we're gonna move on to the second part of this slide here. And the second slide here is about the lotto game, okay, which is the other problem in the exam, but I think most people got this one. I just want to put it here, just kind of phrase it in the terms of what we have already talked about. So in a lotto drawing, numbers are drawn in a non-repeating fashion. This is a clear indication that you have to use something related to factorial. Okay, if you're drawing something and something can repeat, it's not related to factorial. Coin tosses, okay, throwing dice, okay, those things, you can have the same number or the same side of the coin over and over again. So in those cases, it's a clear indication that factorial should not matter at all. Okay? But in this case, when you're drawing numbers out of a lotto drawing, you cannot draw the same number twice, and that's why it is non-repeating. So let's say there are n numbers to draw from, and the lotto game, just need to draw r numbers. The ordering is not important. So if I pick out 1, 2, 3, 4, 5, as opposed to 5, 4, 3, 2, 1, it's considered the same because we only have 5 lucky numbers, and those are 1, 2, 3, 4, 5 in this case. The ordering is not important. As a result, we have this many ways, the combination of picking r out of n items, or n choose r, to draw r items or r numbers from n. The set of all different ways to draw r numbers from n becomes omega, because this is representing all the unique tickets that you can buy for that particular lotto game. Is that okay? So with I think super lotto, or the one in the question is out of 5. We draw 5 numbers out of how many in the exam question? Was it 39 or 35? I cannot remember. It's one or the other.
39.
39? Okay, so that becomes, C 39 R, R is 5. If a prize is awarded when K out of R numbers match, in other words, you have like 3 out of 5 numbers matching, then the set of all tickets that can win this particular prize is the set that we are interested in. okay, this is the set A, there are this number of ways to match K out of R of the lucky numbers. Remember, R is the number of lucky numbers, and K is the number of matches that you need in order to get a partial match for a lower price. Is that making any sense so far? So out of 5 numbers, if you need to match 3, then the number of ways to do that seems to be just the combination, the number of combinations of choosing K out of R items. But wait, hold on a second here. You're choosing 3 out of the 5 lucky numbers to be on your ticket. What about the other 2 numbers? Well, they can be any number, but not just any number. They can be any one of the not so lucky numbers, the non-lucky numbers, right? So that's why this is not the entire story, because you also, for each way to choose K of the R lucky numbers, there are this many ways choosing R minus K of the N minus R not so lucky numbers. And that's why these two need to be multiplied. The product is going to represent the actual number of unique tickets that can win the prize when you match K out of R lucky numbers. Are we still doing okay so far? By changing the actual numbers into variables, it's actually harder to understand. But it also makes it a more general solution. Is that okay so far? In your exam question, N is 39, R is 5, and then K can be either 3 or 4, depending on which part of the question you're answering. Because I just want to relate this explanation to the exam question. Now, this formula also works for winning the jackpot, okay? So in order to win the jackpot for this particular lotto game, you have to match all the numbers. What happens when you have to match all the numbers? Well, in that case, K, which is the number of matches per ticket, has to be the same as the number of lucky numbers. Is that okay? But that's just a special case of what we have already talked about. Because when K equals R, what do we get? When K equals R, what happens to this equation? Okay, let's look at this part here first. When K equals R, what is the number of ways to choose R items out of R items, where ordering is not important? That's exactly one way, okay? So this is one. What about the other part? The other part is, I know in terms of meaning, it doesn't make any sense because we are saying, hey, we have all the lucky numbers, and there's nothing left for not so lucky numbers. But if we just plug in the numbers, let's see if it works out, because it should work out also in this case. What is R minus K when they are the same? 0. How many ways can you pick 0 items out of some number of items? There's only one way, the empty set, right? What is 1 times 1? 1. So there's one way to win the jackpot. Does that make any sense? Yep, it does work out. But you have to be careful about the reverse, okay? In other words, what if K equals to 0? In other words, what if what I want to calculate is how many tickets would have no match to any of the lucky numbers? That's what K equal to 0 means, okay? You have to be careful not to interpret K being 0 to be not winning the jackpot, because that's not what it is. K equals to 0 means none of the lucky, you have a ticket that has none of the lucky numbers. Is that okay so far? Okay, does everybody understand the differentiation between those two cases? Is that okay? All right, well, that's kind of the clarification note that I typed up for the exam questions. I think it's the first one, and was it the last one? Yeah. Okay. Any other questions about this? No questions? All right. If there are no questions about this, we are going to continue with the graph theory stuff. And as I said a little bit early in today's lecture, we're going to go through the encryption stuff, and then we'll move on to state space search algorithms. So we are now on to graph stuff again. And and I was borrowing the notes from somebody else, to talk about cryptography. Let's open up that link. Did anyone read it after the class? Because I think it's just an interesting read.
Started it.
You started? Okay.
It's a pretty long PDF.
It is pretty long, but I'm only interested in the cryptography part because the other part is just talking about terms, and most of those are already in the notes. And they also use non-directed graphs too. All those terms apply to non-directed graphs. So we talked about Julius Caesar's way of doing encryption, which is not very secure because all he did was to shift the letters over by a fixed number for everything that is transmitted. Okay, that's definitely not a very good way to do encryption because you can kind of guess. Okay, first of all, how many ways can he arrange this kind of encryption? The quote-unquote hidden key, there are only 26 possible keys. Okay, and we have a class of 30 people, 50 people, so I can actually assign 2 students to use a potential key to try to decrypt the message. So out of this entire class, out of 26, well, 25 groups, because when the key is 0, it's not a key. So out of 25 groups, 24 of those groups will end up with gibberish, but one group will end up with something that is actually readable. And how much time do you think that's going to take? If someone is to write, a paragraph, say in just regular English, okay, and you are to decipher, the message, how many bytes or how many characters do you think you have to go through before you can come to a conclusion and say whether you have the key or not?
First phrase. First sentence is
First sentence, which is going to be about 10, 15, 20 characters. That's all it takes, right? Because you don't have to decipher the entire message to see that, hey, this doesn't make any sense. Now, with people using all the texting abbreviation, that might take a little bit longer because OMG may actually be OMG, or it may be the encrypted version of something else.
What if you have to pass it through the cipher twice? What if you have to pass it through the cipher twice?
This cipher, if you pass it through twice, like the way it is right now, it's shifting by 3. Passing it through twice means it's shifting by 6. It's not going to help. Yep. In fact, if you have a cipher that shifts by 2 and you do it 13 times, you have just undone the encryption of itself. Because 2 times 13 is 26, so everything goes back to the original. Okay, so not a very good idea. And then the next few slides talk about modular arithmetic. We already know that part. So this one, is using a particular key, and the secret is the key. Okay, in this case, it's using math MATH as the key. So what it does is, assuming A is represented by 0 and M is represented by 12. So the way it does it is to add the original text to the letter corresponding to the key of that position, and then do the modulo math and come up with the final number that is represented. So in this case, A is 0, M is 12, so 0 plus 12 is 12, 12 mod 26 is also 12. So there's a mod 26 that is kind of hidden, like the last one. Well, the last one it does some value out. The math T here, the first T comes from the T of attack, the second T of an attack. The second T comes from the T of the encryption, which is from MATH, the T in MATH. So in each case, T is 19. So you add those two together. 19 plus 19 is 38. When you look at 38, it's more than 26. So you do a mod 26, it becomes 12. So the encrypted text that is transmitted is just going to be an M. So that's how this particular scheme works. Now, with all of these schemes, the secret lies in the key. The key has to be shared by the transmitter and the receiver. Is that making any sense? So if someone is to beat up the sender of the encrypted message until they spill out, what is the encryption key, the whole thing is broken. Does that make any sense? Now, that is even particularly bad if this is a broadcast message. In other words, you're not talking about a party A and a party B trying to send message to each other without people in between knowing what is transmitted. You're talking about party A broadcasting a whole message to the entire world. But only B, as the recipient, is supposed to be able to decrypt it. So in that case, if someone gets the key of the encryption, which is both for encoding and decoding the message, then we have a pretty bad problem, because now the entire world, whoever knows the encryption key can now receive the message and know the content of the message. So that's why we have to get to public key cryptography. How many people kind of know what is a key pair encryption already at this point? Okay, so you have some general idea of what is key pair encryption, at least the principle how it works. So do you guys want to describe how it works, or okay, go ahead.
Like public key, private key encryption, like using a Linux server, for instance. Every user that can sign on to the server has the ability, or has a key. Like only people who have that key can sign on to the server, because they're the only ones that can decrypt the key, the server or the key that the server has. And that's how, like, for instance, it's like how public key, private key encryption for SSH works.
Okay. Okay, so that's good. So what I'm going to do is to kind of explain it again, but using props. Okay. So the problem is So the problem is I want you guys to be able to send messages to me in secret. Okay, so nobody else can see what you are sending to me. Okay. In the class setting, well, that's gonna be a little bit extreme. Okay. But in the setting of let's say healthcare, you need to make sure that you protect the privacy of patients. So if you send an email from if your patient is sending you an email, it is probably a good idea to encrypt that email so that other people cannot eavesdrop and figure out, oh, this person has got this kind of condition and whatnot. Okay. So what I'm going to do, as the doctor in the office, is I have two keys. Okay. I'm the one who used a particular tool to generate these two keys. I'm keeping one key, the black one, as my private key, which I keep in my pocket. The remaining key, the other key, is called a public key, and I'm going to just post this on my internet website, okay, or use some other way so that this is now known to the entire world. So each one of you, if you want to send me a secret message, you can take this key, it's a public key, to encrypt your message and send it to me. When I receive the message, I'm going to use my private key to unlock it to see what is the actual content. Is that okay so far? Okay, so it doesn't seem to be particularly useful as opposed to using only one single key, which is all the other two schemes are about, to encrypt and decipher the message. Okay, but what about this? What about you guys are transmitting the message not using a point-to-point connection? What if you are broadcasting the encrypted message to the entire world? If you use a single key, then we have a problem, because everybody knows how to decipher the message as well, because the same key that you use to encrypt the message is the same key that you use to decipher the message. In the scheme of key pair encryption, everybody has a green key, okay? But when you encode something, or when you encrypt something using the green key, can you decipher using the green key? No, you cannot. That is the whole beauty of a key pair encryption, because now you guys can even share, hey, this is the encrypted message that I sent to TAC. But nobody else can know what you actually typed, because they can look at each other's encrypted messages, but since no one but me, the recipient, has the private key, I'm the only one who can decipher the messages. Is that okay so far? Okay, which is good, because if someone is to come to you and beat you up and try to beat the decryption key out of you, that would be futile, right? Because you don't have any ways to decrypt the message. So that's actually good for you, because nobody's going to beat you up, because they know that beating you up is not going to help. Is that making any sense? So that's the beauty of a key pair encryption. So as a secondary question, okay, so when I share the keys this way, I own the private key, you have the public key. it makes sure that the messages that you are sending to me can only be read by me, which is good. Okay, that's one thing that we need to do to make sure that we have secure communication. The next question is, can someone spoof messages to me?
No.
In other words, can someone pretend to be somebody else and send me a message, and I cannot tell the difference? The answer, no, I can. No, that's actually true. Okay, the key pair encryption scheme does allow, the way it is described, does allow someone to spoof a message, and I cannot tell whether it is true or not. Why is that the case? Because the person who's spoofing also has access to the public key, right? So the person who's spoofing only has to write a message as if that person is one of you, okay, and say, I'm, Chris, okay, and I demand to have a grade like this.
They have to have access to your public key, though, like if they pulled it down through man in the middle for somehow.
What?
The only way they can spoof it is if they have access to the public key.
But that's the whole idea of a public key. I'm going to put it on my website. But that's the whole purpose of a public key, is it can be public. It can be disclosed to the entire world and not cause a problem. It is not a part of this encryption scheme to deal with authentication. It's only used for encryption and deciphering. It's not for authentication. What is authentication?
Digital signatures or certificates.
But what is the purpose? You describe the mechanism. To make sure
that the message that you're getting is actually from the
person who claimed to be sending the message. Okay, so to prove the authenticity of the sender, not the recipient, right? Okay, so how can we make that happen? Using key pair encryption again. Say again? No. This is not going to solve the problem. These two keys cannot solve the problem of authenticity. Because this key pair, okay, because I have already designated this to be the public key, everybody has it already. Okay, so you cannot do much with authenticity. The only thing you can do is to send messages to me that nobody else can read. Only I can read that message. Yep.
One person sending it sends it out and have a signature, like you said.
Right, but how do you make the signature work? That's a good direction. I like where you're heading, so I'm going to pick out 2 additional colors because I don't need it. I got it blue, and just when I need all those other hands that are dried up or too faint, cannot find any. Well, that's okay. I'm going to pick another pen out of my personal collection. Okay, so there we go. The keys that I have already presented, this key pair is something that I generated. I chose to keep this one as a private key, and I chose to disclose this key to the entire world. Is that okay? So let's say Chris is trying to make sure that when I receive a message from him, I can authenticate and say, okay, this definitely came from Chris, or someone who has his certificates. Okay, because somebody can beat up Chris and say, hey, give me your certificate. Okay, so these 2 will now be a key pair that you generate. Okay, so Chris, like me, is going to generate another set of keys, another key pair, which has no relationship to the key pair that I have. Is that okay? So he's going to keep one as a private key, and let the entire world know of the public key. Is that okay? So we're just going to make the assumption that the more expensive pen is going to be his private key, and the entire world knows the public key. Is that right? Okay. So how can this be used for authentication purposes? I know the public key. He has the private key.
You use the private keys to create a signature, right? And so if he creates another set of keys, a private and a public key, and he can give you the public key, he can then create
created a digital signature with his private key, and then when he sends the message to you, you know that it's him because you can only look at his the digital signature with the public key that he gave you. And the two keys are mathematically linked, so you know that
Okay.
you right.
Yep.
Right guy.
Okay, that's good. And you want to add to it?
I was gonna say you could encrypt the message using his public key, and then if he can give you the decryption, you know it's him.
It's the other way around. So what Chris is going to do is, first of all, he's going to compute what we call a digest, or a checksum, or a hash value for the message that he's sending to me. So the hash or the MD, it can be MD5, can be any one of the known, hash algorithm. What it does is it will compress his entire message. So let's say Chris has a really long message to send to me because it's including a screenshot and whatnot, okay? So the entire message is like 20 megabytes. Well, I don't need to look at the entire 20 megabytes. So what he's going to do is he will run his 20 megabytes through a hashing algorithm, and it comes up with a hash value that is much shorter. Let's say 512 bytes. Okay, so out of the 512 bytes, okay, he's going to use his private key, the expensive pen, to encrypt the signature. Okay, so and he will attach the signature to the message itself. The message that he's sending to me may or may not be encrypted using my public key. That's a whole separate thing. If authenticity is the only thing that I'm interested in, I just need his signature. So I would receive his email along with the quote-unquote signature that is encrypted using his private key. What do I have? I have the public key of Chris. So what I can do is now I'm going to apply the public key to unlock the signature that he encrypted using his private key. Okay, so now I get a checksum. Well, it's useless to look at a checksum, which is a random chunk of bits, right? So what I would do is I'm going to use the same public algorithm to compute the checksum out of the rest of the message. If the checksum that I compute matches the checksum that I unlock from his message, then I can establish whoever sent the message has Chris's private key. Now, if he shared his private key with 20 other people, I cannot differentiate amongst those 20 people. I can only tell that the message was sent by somebody who has the private key that matches the public key that I'm holding on to. Is that okay? Now you can do these two things, one or the other or both. In other words, you can just say, I'm going to encrypt a message to send to a recipient to make sure that nobody else can read the message. You can just do that. Or you can just do, I'm going to put a signature on my message so that the person who's receiving my message knows that it comes from me. Or you can do both. So it all depends on what is the purpose and also what is important. Sometimes it's not important to encrypt the message, but it is important to authenticate. And other times it is just the opposite. And sometimes you need both. Are there any questions about the application of key pair encryption? Okay, if there are no questions about key pair encryption, we're gonna skip all the way to the math, okay? Because this stuff here it's okay, but the math stuff is the core part. Okay, this is it. Okay, so this is all about prime numbers. So the way it works is the blue part is the procedure, which is general, and then the green part is an actual application, and obviously we are dealing with tiny prime numbers, okay? So nobody would use tiny prime numbers for encryption purposes. So the setup procedure is you have to find two prime numbers. P and Q are prime numbers, and the N being the product of these two prime numbers. You would have to compute M, which is the LCM, the least common multiple of P minus 1 and Q minus 1. You have to pick a R so that it shares no divisor with M. Okay. You have to find S so that R times S equals to 1 mod M, which is kind of odd because anything mod M, 1 mod anything is 1. Okay. So R times S, has to fit this requirement. So once you figure out these numbers, you would announce N and R to the entire world, but you would keep P, Q, and S as a secret. So we're just working with numbers here. This whole thing is about finding prime numbers with certain properties. Okay, so we'll just kind of condense the blue part, which is kind of complicated, and it's actually the biggest, the most important part of key pair encryption is the blue part. But we'll just kind of condense it to, we just have to find some prime numbers with certain properties, okay? Because the focus is now on how do we do it? So in this particular case, somebody picked P to be 7, Q to be 11, so N equals to 77. 7 minus 1 is 6, 11 minus 1 is 10, so the LCM is 30, because the least common multiple between 6 and 10 is 30. That person will also pick R to be 7, S is 13, so the R times S is 91, and 1 mod 30. 91 mod 30 is 1. That's basically what it is. Okay, so you want the remainder of dividing RS by 30 to be 1. So now we can now announce to the entire world what N is and what R is. So that's the setup procedure. The next slide talks about how do we send a message. So we are sending a message of 89. So for whatever reason, Chris wants to send me a number 89. So how is this going to be encoded using the public key? Well, it's all about power in this case, because the way it is sent, assuming that we are sending 8 individually and 9 individually, so what you do is you use 7 as the power. R is the power. So 8 to the power of 7 mod 77 is 57. The second number, which is 9 to the power of 7 mod 77 is 37. So what is being transmitted are these two numbers. 57 is transmitted in place of 8, and my cursor is over the other number. 37 is transmitted in place of 9. Okay, so that's you can assume the entire world can receive these two numbers. So now the question is, what can I do when I receive the message? When I receive the message, which is 57 as the first number and 37 as the second number, I would compute 57 to the power of 13, take that number and mod it with 77. Now if you do the calculation, the end result of that calculation is 8, which is the original value that Chris is sending. The second value that is transmitted is 37. I will take 37 to the power of 13. If you mod that number by 77, that number will boil down to 9 again. So that's how this whole key pair encryption thing works. What is the the most important part of key pair encryption? Is it the properties of all these numbers, P, Q, R, and P, Q, N, R, S? Is it those numbers? Is it the way we find those numbers, or is it actually those numbers? Which one do you have to keep as a secret? The way to find those numbers, or the numbers themselves? Well, the way to find those numbers is well known. In fact, that's the whole thing about the NSA RSA thing. Does anyone know or want to talk about the NSA RSA thing? I know it's being recorded, but since it's in the news, I think we can talk about it.
So where they use the default,
Right.
Is it where the NSA I think recommended that they use a default encryption algorithm that was potentially flawed?
Yes, it's not the encryption algorithm that they're defaulting. What are they defaulting to? How to generate a key pair. Okay, because if you find the P, Q, R as in a certain way, there's a reason why they have to fit this particular property. Because if it does not fit these properties, it can be cracked relatively easily.
Yeah, by memory scraping, basically. By memory scraping. Like that was the whole point of the heartbeat clock. Yep,
the heartbeat problem, which is related to SSL, and yep. Okay, so are there any questions before you guys go off to get lunch? No? Yep, go ahead.
If you know N, can you figure out P and Q disruptor?
Well, yes, you can. Okay, that's the whole thing.
But it's time
But it's but it is really, really hard. So you have to make n really, really hard to factor. And that's why you pick P and Q as huge prime numbers. Because when you multiply two huge prime numbers, you end up with a huge product. To factor a number like that is going to take time. So the whole thing about cracking RSA encryption is factoring numbers. If you have a really fast way to factor huge numbers into its prime components, you can crack RSA encryption in no time. And people have been looking for ways to do that.